A very good morning all of you. Before we start today's lecture, so let me summarize all the applications of flip-flops. So if you look at here, there are 7 applications mentioned here. There are many more and many other applications. Out of these 7, we already covered data storage, serial, parallel data, data transfer, or the conversion from serial to parallel to serial. First 4 applications that we covered in the shift registers part. So if you remember, data storage can be done with flip-flops. If you want to store 8-bit data, you have to use 8 flip-flops. If you want to use 12-bit data, you have to use 12 flip-flops, and so on. So we have a special circuit for the data transfer, parallel data transfer, as well as serial, or parallel to serial to parallel also. Now we are going to see the next application, 5, 6 and 7. So fifth application is counting pulses or counting binary numbers like 0 to 10, 0 to 9, or 9 to 0, or 0 to 100, up counting or down counting. So in counting, we are going to use the flip-flops in asynchronous and synchronous mode. That means we are going to design 2 types of counting circuits. One is the asynchronous counting circuit, second one is the synchronous counting circuits. And later we are going to see how your frequency division will be takes place. Suppose if you give a 60 megahertz clock, how you can make output as a 6 Hz or 10 Hz depending on your requirement. And last we are going to design the state of machine design. That means here we are going to design the sequential logic circuit. Actually, like whatever we have seen in case of combination logic circuit, we have stated the problem, then we have configured the input and output combinations, then we form the truth table, then we minimize the K map, and finally construct the circuit. In the same way, your sequential logic circuit also starts with one statement, then we give the possible input and output combination, then we select the required flip-flop to design that particular excitation or truth table. Then we connect all the connection based on the expressions achieved through the K map. It is same as your sequential logic circuit. Only thing here we have to consider a clock as well as the memory elements. The rest will be same. So now we'll start with the counters or counting pulses or up counting or down counting. Now let us start with the counter. A counter is a digital circuit which going to count a event or a pulse or maybe a certain thing, either incrementing fashion or decrementing fashion, either it may be increasing order or decreasing order. If you want to understand a simplest fashion, let us take a token number system. If you go to any bank or any hospital, you will be given some token number, and doctor will press the button. The moment he press the button, your counter number, your token number will change to the next number. So if it is 5, then goes to 6, then 7, it goes on. Similarly, when you go to the bank also, you will have the same kind of situation where you will be given a token number and your token number will be called. So there you use the counter. In these 2 places, your counter giving the number of persons attended a treatment or number of persons used their service in the bank. Or if you go to the traffic signal, in traffic signal, it is going to count the number of seconds, 23 seconds or 24 seconds. So in this case, it is measuring time. In this case, number of people attended medical service. In this case, number of people attended the bank service. So similarly, there are other applications, like if you go to your home appliances like your washing machine, your microwave oven, there also your counters will be there. You will set the time. So the set time is nothing but a counting kind of thing. It is going to count from 60 seconds to 0 seconds or 0 seconds to 60 seconds. Or your washing machine, you program it for 2 hours 30 minutes, your counter will start. And similarly, your digital watches. And if you go to industries, so your products, the manufactured products will be moving on a conveyor belt. You are going to use a simple circuit. So where you are going to send light from one side of the conveyor belt to other side of the conveyor belt. In the middle you will be moving your objects, maybe bottles, maybe products. Whenever light obstruct, your counter will increase its count by 1. So it is indirectly measuring the number of products that pass through the particular belt. Similarly, if you go to parking places, there will be a counter which counts the number of vehicles in and out of a particular parking lot. Or if you go to any mall, you will be having a counter at the entrance, the number of people in and out for that particular day. So if you consider in this way, there are many more applications of counters in everywhere. Wherever you need to monitor a certain parameter, either it may incrementing order or decrementing order. So this is all about your introduction to your counters. Now we'll see the designing part, how we are going to design the incrementing counting and decrementing counting in a moment.
Now let us start with the counter classification. Your counters are mainly classified into three categories. The first one is asynchronous counters. And there will be synchronous counters. And third one is a shift register counters. You are going to have counters based on shift registers also. In asynchronous counters, you are going to have up counter, down counter, or up down counter in the same circuit. Same thing with synchronous also, but shift register, there is a different. This is slightly different counting pattern that we will see when we discuss the shift register counters. Now we will see the basic difference between asynchronous and synchronous counters. In asynchronous counter, you are going to have flip-flops, set of flip-flops in which clock is given to only first flip-flop. Your clock will be given to first flip-flop. Second flip-flop will react with the output from the previous flip-flop. The output from the previous flip-flop will act as a clock for the second flip-flop. Similarly, output from the second flip-flop will act as a clock for the third flip-flop. That means your clock is given to only first flip-flop. Whereas in synchronous case, all the flip-flops will be given to the clocks at the same time or simultaneously. The same clock will be given here and same clock will be given here. This is the major difference between asynchronous and synchronous, even though both are synchronous with the clock, but how the clock is given differs. Now in this case, when you want to do any counting operation, this is slow because this flip-flop will respond only whenever this output is going to make transition. Similarly, this flip-flop will respond only whenever this make transition from 0 to 1 or 1 to 0 depending on which clock pulse you are using, positive edge clock or negative edge clock pulse. So that means it is going to be little slow. Whereas in this case, all the flip-flops are connected to the clock at the same time. So all the flip-flops will change their state at the same time. So it will be a faster. This is the first difference. So this is a second difference, like this is a slow process and this is a fast process. Now we'll see the third point. This circuit will be simple in design. This circuit design will be complex. Let's take the fourth point. The propagation delay will be larger. The propagation delay for the asynchronous is large because you are going to apply clock to only first flip-flop. Second has to wait till the first output changes. Third has to wait till this second output has to change. Whereas in this case, the propagation delay is very less. Propagation delay is less. So these are the major differences between asynchronous and synchronous. Now we'll try to see how to design the asynchronous counters. Now we'll start with the asynchronous. Asynchronous up counter. Asynchronous up counter means you are going to design a circuit which is going to count 0 to 1 and 1 to 2 and so on till whatever the number you want. It is going to be in the ascending order. First we'll start with the 2-bit counter. So please remember, 2-bit counter is nothing but you are going to have two binary bits. Two binary bits can take 0 0 0 1 1 0 1 1. This will be equivalent to 0 pulse. first pulse, second pulse and third pulse. It is nothing like a counting in decimal like 0, 1, 2, 3. So now we are going to design a circuit which is going to count in this sequence. So at any point of time, the output of the flip-flops will give you either 0 or 1 or 2 or 3. So since if you look at here, you need to store 2 bits. One for the MSB, one for the LSB. So we need 2 flip-flops. So let me take 2 flip-flops. The first flip-flop will store a Q0 and second flip-flop will store a Q1. If you assume this is your Q0 and this is your Q1. So this is my Q0, this is my Q1. Now if you observe carefully, once again let me write it here. If you observe carefully, this is toggling, again toggling, again toggling. That means we can use T flip-flop or JK flip-flop with J equals to 1, K equals to, this is nothing but again a T flip-flop only. For the simplicity, we assume we are going to take JK flip-flop with both inputs are connected to the 1. So let me take the first flip-flop here. Let me connect it to the VCC. That means logic 1. And I am giving clock to this flip-flop. I am making it a positive edge triggered clock. Now if you run the circuit, your Q0 will change for every clock pulse. That means for the first clock pulse it move from 0 to 1, second clock pulse 1 to 0, third clock pulse 0 to 1, and it will be toggling in the loop. Now we need to change the second flip-flop output. If you observe the second flip-flop output toggling only whenever, so this is toggling 0 to 1 whenever your Q0 is going from 1 to 0. So since this is also toggling from 0 to 1, I can use JK flip-flop with input 1 for this also. I am going to use again one more JK flip-flop which also connected to the power supply. That means both are 1 1. Your J is 1, K is 1. Here also J is 1, K is 1. Now we need to give the clock. So since I said I am going to use a positive transition clock, if you look at here, your Q0 is going from 1 to 0. At this place your Q0 is going from 1 to 0. If you look at here, your Q0 bar, it will go from 0 to 1. So that is a positive going transition. That means I can take my Q bar from here. This is Q0 bar. I can give this as a clock to the second flip-flop. So this is very important. I am taking Q0 bar as a clock to the second flip-flop. If you look at here, your second flip-flop will toggle only whenever Q0 goes from 1 to 0. There is nothing but whenever Q0 bar goes from 0 to 1, because this acts as a positive going transition to this second flip-flop. Now if we start analyze this circuit, let's take clock 0. Let's take Q1 here and Q0 here. Let us assume first both are 0 0. When the first clock is applied, here flip-flop 1 and this here flip-flop 2. So this is Q1. When the first clock is applied, if you look at here, the first flip-flop is connected to VCC, that means both 1 1 and your clock also high. This will toggle your output, that means your Q0 will toggle to 1 state. But if you look at the second flip-flop, so whenever your Q0 move from 0 to 1, whenever your Q0 move from 0 to 1, your Q0 bar will move from 1 to 0. Whenever it moves from 1 to 0, your second flip-flop will not respond because it is going negative clock transition. As a result, it will be in the same state, that will be in 0 state. Now when the second clock pulse apply, your Q0 will move from 1 to 0. Whenever your Q0 move from 1 to 0, your Q0 bar will move from 0 to 1. That means it's going to give a active clock pulse to the flip-flop. In this case, your 0 will toggle to 1 state because your J and K are again connected to the power supply. Okay. Now if you take the next clock pulse, again a next clock pulse, your 0 becomes 1. Whenever it goes from 0 to 1, your Q bar will move from 1 to 0. When it moves from 1 to 0, your flip-flop 2 will not be active, so it will be in the same state. Now when the next clock pulse comes, your first flip-flop again toggle to 0. Now your Q0 bar is moving from 1 to 0. Now your Q0 is moving from 1 to 0. That means your Q0 bar will move from 0 to 1. That means it's going to give active clock pulse to the second flip-flop. Now it becomes 0. So you started with 0 and ended 0. This is one full cycle. This is like 0, then 1, then 2, then 3, again 0. Again, if you further, it will be again repeat the same cycle. Now I will show the simulation of this circuit. Then we will proceed to the higher order asynchronous up counters. Now we will try to simulate the 2-bit up counter. As I said, 2-bit up counter required 2 flip-flops. I taken JK flip-flop. And if you look at carefully, my J and K are connected to the input switch. Here also same thing, J and K are connected to input switch. When I am going to simulate, I am going to make J and K as 1. So that it acts as a toggle flip-flop. Whenever the clock signal comes, they are going to toggle depending on the positive going transition or negative going transition. And if you look at here, I connected my preset to one control input and clear to other control input through a common switch, so that I can preset my 2 flip-flop outputs to either 1 state or clear my flip-flop outputs to the 0 0 state. Now we'll try to run the simulation. If you look at carefully here, my Q bar is connected as a clock to the second flip-flop. That means whenever Q go from 1 to 0, your Q bar will move from 0 to 1. Whenever it goes from 0 to 1, this flip-flop will receive an active clock pulse and it will produce the desired output. Now we'll run the simulation. Now if you look at here, there is a warning here. The both preset and clear are active at the same time. So we should make it both 1 1. So whenever both are 1 1, your flip-flop will take its normal action, JK flip-flop action. As I said, you cannot keep both 0 0 because you are asking your flip-flop to set and reset at the same time. Now you kept your preset also 1, clear also 1. That means your preset clears are disabled. Now it's going to do the JK flip-flop action. Now my clock is connected. Let me reduce my frequency to 0.5 Hz. That means every 2 seconds you are going to see the change. Now since J and K are 0 0 and your J is 0, K is 0, it will be in the same state for forever. The moment I make my J equals to 1, K equals to 1 and clock is active, it's going to toggle between 0 and 1 with the frequency of the clock. Now we'll run the simulation. Now it is 0 1, then 1 0, then 1 1, then again 0 0, then 0 1, 1 0, 1 1, then 0 0. This is my LSB and this is my MSB. Please look at the counting sequence. 0, 1, 2, 3 and 0. So this is how your circuit is going to count from 0 to 3. So whenever I will make my JK equals 0, it will be in the same state. Now I can clear. If I want to reset my counter to 0, so what I can do, I can clear it. Now as my counter is clear, again I can start my counting by making J equals to 1 and K equals to 1. So it is very clear, it is counting from 0 to 3. This is for the 2-bit up counter. Now we'll try to increase to the 3-bit and 4-bit in a moment and we'll see the simulation.
Now let us analyze the waveform analysis of 2-bit up counter. So this is a diagram which we already discussed. Now we'll see this is your clock This is a updated clock. Now if you try to write the output waveform for Q0, let us assume it is already in the initial state. This is the initial, it is 0. The moment when you encounter the first clock pulse is toggle to 0 to 1, and it will be in the same state till the next clock pulse comes. At this clock pulse again toggle from 1 to 0, and it will be in the same state till the next clock pulse comes. So every clock pulse, every positive going clock pulse, your Q0 going to toggle. This is your Q0. You can clearly see every clock pulse toggling 0 to 1, 0 to 1 and 0 to 1. 0 to 1, 0 to 1, 0 to 1, or 1 to 0, 1 to 0, 1 to 0 whenever you are taking a active positive going edge. Since as I said, my circuit is a positive edge trigger, so my Q0 will toggle every time. Now your second flip-flop, this is related to flip-flop 1. Now we'll take the Q1, this is related to flip-flop 2. So if you look at here, your flip-flop 2 will toggle whenever your Q0 bar goes from 0 to 1. To get the idea, so I had drawn a waveform for the Q0 bar also, which is exactly opposite to your Q0. If you look at here, this is your Q0 and this is your Q0 bar. Now your Q1, so initially at 0. So whenever your Q0 goes from 0 to 1, this will toggle 0 to 1. Again here also it is going from 0 to 1, again toggle from 1 to 0. So this is how you can analyze the waveforms. It is very clear. First flip-flop will toggle every clock cycle, second flip-flop will toggle whenever your Q0 bar goes from 0 to 1. That is nothing but a positive going clock transition for the second flip-flop. Similarly, we can extend this discussion to 3 flip-flops, 4 flip-flops. The same thing, if you have one more flip-flop, if suppose you are having one more waveform here that is related to your Q2, your Q2 will toggle whenever your Q1 bar goes from 0 to 1.
In case of 2-bit counter, we are able to count 0 to 3, but in real time we may need to count more than that. So let's take the 3-bit counter. 3-bit counter means it can measure or it can count from 0 to 7. That means all zeros to all ones. If you look at here, you need to store 3 bits. That means you require 3 flip-flops. So let me take my 3 flip-flops here. You can take any other flip-flop. The easiest one will be toggle flip-flop or JK flip-flop with J equals to 1 and K equals to 1. So I am taking my JK flip-flop with J equals to 1 and K equals to 1 are connected to the power supply. I am taking the same this one and connecting here as again J and K. We are going to use the toggling action for designing the counters. That's why I told you the toggling action is very important when you design the counters. Now we'll start the counting sequence. So it will start with first all zeros. Let us assume this is your Q0 flip-flop output, this is Q1 flip-flop output, and this is your Q2. So this is my Q2, this is my Q1, and this is my Q0. So it starts from 0 0, then 0 0 1, 0 1 0, 0 1 1, then 1 0 0, 1 0 1, 1 1 0, and all ones. Now you observe carefully, the first flip-flop is toggling every bit 0 to 1, 1 to 0, 0 to 1 and 1 to 0 and so on. That means your clock supposed to be given to the first flip-flop, so that again I am giving a positive edge trigger clock, so that your first flip-flop will toggle for every clock pulse. Now if you look at the second flip-flop is toggling whenever your first flip-flop goes from 1 to 0, 1 to 0. Then if you observe carefully, whenever this is moving from 1 to 0, your Q1 is making the toggling. So it means whenever Q moves from 1 to 0, whenever your Q0 moves from 1 to 0, your Q0 bar will move from 0 to 1. So this signal will act as a clock for the second flip-flop. Then only we can toggle in an appropriate way. So what I'm going to do, I'm going to take my Q0 bar and I'm going to give this as a clock to the second flip-flop. This second flip-flop will toggle whenever your Q0 bar move from 0 to 1. This will happen whenever your Q0 move from 1 to 0, 1 to 0 and 1 to 0. Now if you look at the third flip-flop is toggling whenever your Q1 is moved from 1 to 0. If you look at here, this moving from 0 to 1. Whenever your Q1 moves from 1 to 0. If you look at here, 1 to 0 happened only once. If you look at it, this is only one place. Your Q1 is moved from 1 to 0. That means your Q1 is moved from 1 to 0. At the same time, your Q1 bar will move from 0 to 1. So I'm going to take my Q1 bar and made as a clock for the third flip-flop. So if you look at here, whenever your Q1 moves from 1 to 0, your Q1 bar will move from 0 to 1. This will act as a clock for the second flip-flop, and second flip-flop going to make the transition from 0 to 1. Rest all other places, if you look at here, this is 0 to 0, 0 to 1, 1 to 1, 0 to 0, 0 to 1 and 1 to 1. There is nowhere it is having transition other than this particular place where you are having circuit. Now this circuit is going to count from 0 to 7. So what I can do is I can take my Q0, Q1 and Q2 to a 7 segment display. So 7 segment display require 4 inputs, A, B, C, D. Now consider A is my LSB and D is my MSB. Since I don't have fourth input, I am going to make this as 0 and I am going to connect my Q0 to A and Q1 to B and Q2 to C. So it is going to display a 0 to 7. Now we'll try to see the simulated circuit, how it is going to display all those numbers right from 0 to 7. So logic you should, the only logic you should remember is under which condition your first flip-flop will toggling. So the first flip-flop will toggle for every clock cycle. If you look at here, it is alternate 0 and 1. Your second flip-flop will toggle only whenever your Q0 bar moves from 1 to 0. This will happen only whenever your Q0 moves from 1 to 0. So this is a positive. See, as I said, I am going to use a positive edge clock transition. So we have to give the same positive edge clock transition to the second flip-flop also, and here also same thing. So whenever your Q1 moves from 1 to 0, your Q1 bar move from 0 to 1. At that particular instant only your second flip-flop will react. Now we'll try to run the same circuit with the simulation with the 7 segment display in a moment. So this is my circuit. This is a 3-bit up counter circuit. So 3-bit up counter circuit, 3 flip-flops and 3 flip-flops J and K are connected to the control switch, which I am going to keep it 1 whenever I want to toggle the flip-flops. If you look at it, this J also connected to this control switch. This J also connected to this control switch and this J also connected to this control switch, and my preset is connected to all the preset input of the 3 flip-flops. Similarly, my clear also connected. This is my clock which I am going to apply to the only first flip-flop. This is my Q0, Q1 and Q2, and a Q3 I made it here and I made it completely 0, and these 4 inputs I connected to a BCD to 7 segment display. That means these four inputs you can consider as a BCD equivalent number. Like if you look at it, this is your A, B, C and D, and these 4 going to produce the decimal display when you run the simulation. Now we'll try to run the simulation. As usual, you can see if you look at here, second flip-flop clock is generated from the Q bar or Q0 bar, and second flip-flop clock is generated from the Q1 bar. Now we'll run the simulation. Now let us run the simulation here. Now let us clear all the flip-flops with 0. Now my flip-flops are clear to all zeros. If you look at here, my decimal display also showing 0. Now I'm going to make my clear to 1. That means all the flip-flop going to do the JK flip-flop operation. Now I'm going to switch on my J equals to 1 and K equals to 1. The moment I make J equals to 1, K equals to 1, my counter start count from 0 to 7, then 7 to again 0. Let will run the simulation. I made my clock frequency as 0.58. That means every 2 seconds you are going to see the change in the decimal number. Now you can clearly see. First you look at the binary equivalent. Then you see the decimal display. So let will clear it once. We will start from 0 once again. Now 0, then 1, then 1 0 will be 2, 1 1 will be 3, 1 0 0 will be 4, 1 0 1 will be 5, 1 1 0 will be 6, 1 will be 7. So the same thing we can see in the decimal display also. 1, then 2, 4, 5, 6 and 7. So if you have a 3 flip-flops, you are going to count from 0 to 7. If you are having 4 flip-flops, you are going to count from 0 to 15. That means 0 to F. That we will see in a moment. So this is a 4-bit up counter. The logic is same. Your first flip-flop will toggle for every clock cycle, every 1 clock cycle. Your second flip-flop will toggle whenever your Q0 bar goes from 0 to 1. Your second flip-flop will toggle whenever your Q1 bar moves from 0 to 1. Similarly, your fourth flip-flop will also toggle whenever your Q2 bar move from 0 to 1. And you can see here same thing. I connected preset to all the flip-flops and clear to all the flip-flops. And these are my Q0 to Q3. If you assume these are four BCD outputs, then this can be given to a 7-segment display. This 7-segment display will display from 0 to F, that we are going to see in a moment. And this is my JK input. So whenever I want to run the counting operation, I am going to make my J equals to 1 and K equals to 1. Now let's run the simulation. Now if you look at here, my both preset and clear are 1 1. So let will clear the flip-flops first. So now I cleared my flip-flops. Now you can see all the flip-flops were 0 0. Now the counting start from all zeros to all ones. The moment I make my J equals to 1 and K equals to 1, it's going to take the counting. The same counting sequence you can see in the display also. Let will start the counting process. Now 1, then 2, 1 0, 1 1 will be 3, 1 0 0 will be 4, 1 0 1 will be 5, 1 1 0 will be 6, 1 will be 7, then 1 0 will be 8, 1 0 0 will be 9, 1 0 1 0 will be 10. 10 is nothing but A, then B, then C, then D, then E, then F, then 0. So this cycle will repeat as long as you provide the clock signal. So this is how you can design the up counters. So wherever I want to reset my counter, suppose if I stop here, now 7 is there in my registers. Now 7 is the output display. I can reset it to 0. Again I can start my counting from 0, 1, 2, 3 and so on. So if you look at here, it is going on. Whenever I keep my J equals 0, K equals 0, it will be in the same state. Now it is at the 6th state. Whenever I resume this one, again it's going to count from the same number like 7, then 8. Even I can stop here. 9. Whenever I make it this 1 1, again it goes to the A state. Whenever I want to reset, I can stop, just reset it, and again start from 0, 1 and so on. So this is how you are going to design the asynchronous up counters, where it is clearly seen your clock is given to only first flip-flop. The second and third and fourth flip-flop are got their clock from the previous flip-flop output as a clock to the next flip-flop. So this is how we are going to design 3-bit, 4-bit, 5-bit. Suppose if you want to count 0 to 32, then you can use the 5 flip-flops. If you want to measure for 64, then 6 flip-flops, and connection will be same. Only thing is we need to add extra flip-flops so that we can measure any number depending on our requirements. This is all about your up counting. Now we are going to see the down counting, how it is going to do the action.
Now let us design the 2-bit down counter. So down counter means it's going to count in the descending order. That means count start from 3, then goes to 2, then 1, then 0, then again back to 3. So you're going to count in the descending fashion. Since you're having a 2-bit down counter, it can have both 1 1, that will be equivalent to 3, then 1 0 will be 2, 0 1 will be 1, and 0 0 will be 0. So this I am assuming Q0 flip-flop output, this output of first flip-flop, this output of second flip-flop. So since we need to store 2 numbers, I am going to take 2 flip-flops, one flip-flop for Q0 output and another flip-flop for a Q1 output. So as usual, I am going to take JK flip-flop with the toggling action. That means I am going to connect my J and K to the logic 1 or power supply plus VCC. Same thing here. So all the counters mainly designed by T flip-flops. So this is my J and K. Now I am going to analyze my transition. So when I want to count from 3 to 0, if you look at here, the Q0 output changing 0 to 1 to 0, 0 to 1 and 1 to 0. It is toggling for each next transition or each clock pulse. So that means you should give clock to the Q0. So this is my Q0 output. So I am going to give positive edge triggered clock. So if you look at this, only this particular portion, for every clock pulse, your Q0 will toggle to 0 to 1 and 1 to 0 as long as your clock is enabled. If you look at the second flip-flop is toggling to 1 to 0 whenever your Q0 is moving from 0 to 1. That means whenever your Q0 moving from 0 to 1. So this is a positive going transition. So whenever this is happening, your Q1 is getting toggled from 1 to 0. That means I can directly use Q0 as a clock to the second flip-flop. In the previous case, when you are counting downside, your Q0 was moving from 1 to 0, but in this case is moving from 0 to 1. That means I can use my Q0 as clock to the second flip-flop. If you look at here, whenever your Q0 move from 0 to 1, your second flip-flop will toggle to 1 to 0, and this is my Q1 output. Now let us analyze with the clock. This is Q0 and Q1. Let's clock here. So let us assume both the flip-flops in 0 0 state. Before any clock gives, let's give the first clock pulse. When the first clock pulse given to Q0, so this will toggle to 1. Whenever this toggle from 0 to 1, so if you look at here, your Q0 is given to the second flip-flop. Whenever this moves from 0 to 1, that means it will act as a clock to the second flip-flop, active clock. So it also going to toggle from 0 to 1. When the second clock pulse happens, your Q0 again toggle to 1 to 0. This is 1 to 0 transition. That means this will not activate the second flip-flop. That means it will be in the same state. In the next clock, your Q0 will toggle from 0 to 1. Now your 0 to 1 will activate the second flip-flop, then toggle to 0. In the next clock pulse, your 1 becomes 0. So when it moves from 1 to 0, this is not an active clock pulse, the second flip-flop, it will be in the same state. If you observe here, this will be 0, 3, then 2, then 1 and 0. So this is how it is going to count in the downwards fashion. Suppose if you want to increase the count sequence to 0 to 7, what you do is you add one more JK flip-flop Now you are going to take the clock from your Q0 to your Q1 to next flip. Suppose you want to make a 3-bit which count from 7 to 0 like downwards. So you are going to do the same circuit. Your 3 flip-flops will be taken for 3 bits. So as usual your J and K will be 1 1. Your J and K will be given to 1 1 or VCC. Same thing here. Same thing. Only thing is you are going to give clock to the first flip-flop. Second flip-flop clock will be generated from the first flip-flop Q output. Similarly, third flip-flop clock will be generated from the Q1 output. Now this is your Q0 and this is your Q1 and this is your Q2. This is going to count in the downwards fashion 7 to 0. Similarly, if you want to go for the 4-bit, then you have to add one more JK flip-flop and add this Q2 as a clock to the 4th flip-flop. Then it is going to count from F to 0. Now we will try to simulate this circuit and try to see how it is going to count the downwards counting. Now let us simulate the 2-bit down counter. You can see here whatever the circuit we discussed just now, the same circuit. I have taken two JK flip-flops and whose J and K are connected to the power supply or VCC, or I can make a control input which can be made 0 or 1 depending on our requirement, and preset and clear are connected. This is my clock. If you look at the major difference, this time my Q is connected as a clock to the second flip-flop. In the previous case my Q bar was connected as a clock to the second flip-flop. Now let's run the simulation. Now nothing is visible. We'll set the flip-flops to 0 0 state by using clear input. Now my flip-flops are set to 0 0. The moment I make my J equals to 1 and K equals to 1, my counter going to start counting. Till that part it will be in the same state, because for JK flip-flop J equals 0, K equals 0 will be the memory state. Let me make my clock frequency as 0.5 Hz. Now let's make it J equals to 1 and K equals to 1. Now you can see your counting start from 3, then 2, 1 0 means 0 1 means 1, then 0 0, again it goes to 3, 3, then 1 0 will be 2, 0 1 will be 1 and 0 0. This is my MSB and this is my LSB. Now if you look at clearly, this is counting in the downward direction, 3 2 1 0 and 3. This is for 2-bit. If you increase to 3-bit, you are going to add one more flip-flop. Your preset going to be extended, your clear going to be extended. This time your Q will be given as a this time your Q will be given as a clock to the third flip-flop. That we'll see in a moment. If you look at here, for the 3-bit down counter, everything is same. We added just extra flip-flop, and for this flip-flop the output of the second flip-flop Q is connected as a clock to the second flip-flop, because if you take the counting sequence, for 3-bit down counter, so 3-bit means you start from all ones, then 1 1 0, 1 0 1, 1 0 0, 0 1 1, 0 1 0, 0 0 1 and all zeros. If you look at here, your Q0 is toggling for each bit, 0 2 1, 1 2 0. That means your Q0 will be connected to the clock, and your second flip-flop is toggling whenever your Q0 moves from 0 to 1. Your second flip-flop is toggling from 1 to 0 whenever your first flip-flop toggle from 0 to 1. Whenever your Q0 moves from 0 to 1, your second flip-flop will toggling. Similarly, if you look at the third flip-flop is toggling 1 to 0 whenever your second flip-flop moves from 0 to 1. Whenever your Q1 moves from 0 to 1, your third flip-flop is toggling. So that's why we are given Q0 as a clock to the second flip-flop and Q1 as a clock to the third flip-flop. If you look at here, same thing, your Q is given a clock to the second flip-flop and this Q is given clock to the third flip-flop. This is my LSB and this is my MSB. I have connected these three inputs as three inputs to the BCD to 7 segment display, and fourth one I make it as completely 0. Now this decimal display going to display 7, 6, 5 in the downward direction. Similarly, the binary equivalent also will count in the downward direction. Now we'll run the simulation. Now I'm going to first clear my outputs of all the flip-flops. So I'll make all the zeros. So you can see my decimal 0. Now I'm going to make both 1 1 so that my JK flip-flop is ready for the action. Now I'm going to make my J equals to 1 and K equals to 1. The moment I make J equals to 1, K equals to 1, I'm going to start from 7. So you can see start from 7, then 6, then 5, 4, 3, then 2, 1, and all zeros. Again goes to 7 means all ones, 6 means 1 1 0, 5 means 1 0 1, 4 means 1 0 0, 0 1 1 will be 3. So wherever I want I can stop. Let me stop and let me show you. So I stopped here. My J equals 0, K equals 0 now. That means it will be the memory state. I can reset my memory to 0 by using clear. Again I can start from down counting 7, 6 and so on. This is with 3 bit. Same thing can be implemented with 4 bit. That will count from F to 0. That we'll see in a moment. Now this is the 4 bit. The same thing. I added one more extra JK flip-flop, and the output of the third flip-flop is given as a clock to the fourth flip-flop. And this time I connected this my 4 outputs to the BCD to 7 segment display. Now this counter is going to count from F to 0. Let will clear the flip-flop output first to all zeros. So if you look at here, I made all the zeros. I can see 0 now. My J equals 0 and K equals 0 now. That's why it is showing only 0 state. The moment I make J equals to 1 and K equals to 1, it is going to start from F. Now you can see at the equivalent, it will start from all ones. You can see start with all ones, then F, then E, then D, then C, then B, A, then 9, 1 0 0 1, 8, 1 0 0 0, 7, 0 1 1, 6, 0 1 1 0, 5 and so on. So it will be in the down counting process forever in the same loop. So let will stop here. Let will make my frequency to, let's say 3.5 Hz. It will be little faster. We'll see how it's going to be. Make our measurements. Now you can see it is moving at a greater speed. So starting from F and going to the 0. And same binary equivalent is changing in the display also. This is how we can design up counter and down counter using a JK flip-flop or toggle flip-flop.